Seemed a lot today compared to last week. Maybe a few more people will come in a couple of minutes, but in the meantime, how is everyone feeling about the material so far? Uh, Able to keep up? Everything makes sense? Okay. Uh, do you guys want me to go like faster, slower? Up? Forget faster, probably not faster. I do understand that it's a bit dense, the amount of information that's in one uh, class. Um, it is a 12-week class, so I do have to cram in a bunch of stuff initially before we can get to the fun stuff. Uh, like I'm sure all of us want to do classification and detection and things like those. Um, think we should get there next week. Um, if we go at the same pace. Okay, I'll bring that up at the end of class maybe. If I still have it. I do, right? Yeah. Yeah, right. So first homework is gonna cover some of the basic operations that we talked about until last class, and I'm aiming to get that out tomorrow. Uh, Um, so there'll be programming assignments, and while they're doing it, I feel like that would help build intuition for what you should be doing. And I'll also maybe add in links to things that you can refer to with examples. Or if I don't find anything good, then I'll probably do like the pen and paper equivalent of what you would have to do in code as a few toy examples, and then you could build on those. Is that? Yeah, I'll do that. So I'm not really going to be uh, evaluating you based on like how performant their solution is initially. So there'll be multiple ways to do stuff, either with like vector broadcasting type operations or just for loops. So whatever you do will be good as long as like the core principle you're able to execute that. Examples, I'll do that. Thank you for letting me know. Okay, I'll start in just a second, but just briefly, my objective with the way that I'm structuring it is to give you a sense of a lot of these operations, you're not going to have to do them directly by hand because it's already implemented. So like in the workplace, when you're trying to build a project, these are things that you would you would want to know what they're doing under the hood for the case when something doesn't work like you would expect. You would be able to figure out what the like physical reason is for something not working if it's not a code problem, but sequence of operations or what size of convolution window you're using, stuff like that. So things like rotating, translating, you're not going to be writing code to do those things by hand in a real world scenario. Okay, let's get started. Today we'll be talking about image processing. So this is part of the name of the course, computer vision and image processing, and they sound pretty similar. We've touched a little bit upon what computer vision refers to, in that we're trying to extract meaning from the real world, from a scene. So but what's the need for a second term, image processing, when we already have computer vision as a term to describe it? Um, it's more than just words. The origin of image processing was around a lot longer than what we call computer vision today combined. It started off as a bunch of techniques that were used in the ECE sphere. Um, and the reason this is important to us is because it informs us about how they used to think about all of these operations and helps put what we do today in perspective relative to that. It's a little bit different the way that they conceptualize a lot of the operations and how they arrived at those. So one of the key insights is that images can be thought of as signals or functions. And this was before we cared about reasoning about what is within an image, but the field was just starting out, and we still use a lot of techniques from then. So why should we care about all of those things? I'm sure you've at least heard of something like YOLO V8 or a convolutional neural network, ResNet. It's okay if you haven't, but a lot of the things that we have almost ready access to with apps or like Google Lens, you can just throw an image into this magic pipeline that just gives you whatever answer you're looking for. Um, but there's still reason for us to be aware of all of these principles, because when we deviate from what these standard problem formulations and their solutions are, then things start to get weird, things break. So you need to know how to account for changes in images. So if your acquisition, if you had very varying light sources, intensity changes all over the place, your camera will have a gain adjustment setting that automatically adjusts exposure depending on how bright the scene you're looking at is. Those things will make it harder to apply something off the shelf directly. Um, if you take the case of a fisheye lens that you put on a camera, you would end up with a very distorted image, and then to try to apply something off the shelf, odds are it's not going to work for the same thing, because usually we deal with flat, natural scenes. So to be able to account for those sort of differences, and also just when you're not looking at visible light, if it's a thermal image, then those look different. Um, if it's LiDAR, you have a point cloud instead of a flat 2D image. So a lot of these solutions wouldn't generalize to something off the shelf, and we need to be able to reduce as much of those variations as we can to be able to apply these. And we do that by pre-processing an image to try to match it to whatever would be expected by a solution that you're using. So to think of an image as a function, a function in math is something that maps one domain to another, right? You could also think of it like a standard function in a programming language where you have a function definition that consists of a name, which in this case we don't really care about, and it'll take in two arguments and return a value. So you could think of an image as a function that expects coordinates and returns a pixel intensity. And that's for one pixel, and then you pass in an entire array, and it does the same thing for every element in the array. So this visualization, I took the middle row of this image and just plotted the intensities. And so this is the value of the function along that particular row. So it varies over space. Images as signals. When you think of a signal, what comes to mind? It's usually something like radio or sound or whatever, and you would describe those using amplitude, frequency, and time. And this is something that we'll talk about next class, but this, you have a composite signal at the top, and you're able to decompose those composite signals into regular discrete components. So you're able to separate two well-defined signals that would then form the composite signal that you have. And this is done using the Fourier transform, which we'll talk about next class. So to draw parallels with that to images, I showed you this visualization earlier. So the middle row, I plotted that as a heat map just to see what the pixel intensities are. This is from the picture of Arnold as the Terminator again. I applied the Fourier transform to this. It's not important to know how that works at the moment, but basically I'm decomposing it into how often pixel values repeat. And the x-axis is cycles per pixel. So it's essentially, you have a value, say 24 followed by 16, 4, 7, and then 24 again. Not a great example. So at this point, I would say that one cycle was complete because this value repeated. If instead I had the same value repeating twice, then this would be 2 cycles by the time I get to this pixel. So counting the number of repetitions, basically, that gives you the frequency of values along that row. And then I take the 10 ones that reoccur the most, and then I can put them together to get an approximation of what the intensity values was. So just a demonstration of the use of thinking of an image as a signal. Now to get to the actual stuff that we can use, pre-processing. So we have a few example operations that we would like to be able to do. There's things like exposure correction, color balancing, denoising, sharpening, straightening. And we're going to look at how to do these today. So there's two kinds of operators that we can use. There's point operators and there's neighborhood operators. From the name, a point operator, you would guess, is something that works on a pixel. And the reason for the distinction between a point operator and a neighborhood operator is a point operator doesn't care about any of the pixels other than the one that it's operating on. So if you want to make a pixel brighter, what do? Someone. How do you do that? So you would add something to that pixel, right? Um, doesn't depend on what's around it. Same thing for colors. If you know what your color space is and you want to change colors, then you would be able to do that by adding something, taking something away from the color channels if it's RGB, or um, just adding a fixed value to the hue channel if we're talking about HSV. Compositing and matting, I think it would help with visualizations and histograms, so I'm not going to go into those now. Pixel transforms, there's some formal definitions, so it's not complicated really. Either the entire image or an individual pixel, you pass that through a transform, and you get the transformed value. That's it. So you don't care about the neighborhood. There's typically two ways to do these. You either add a constant or multiply by a constant. Adding it, when you're adding something, you would call that a bias. And when you're multiplying something, you usually call that gain. These are, again, terms that come from the signal processing ECE space. So the example over here, I have my original image. I generated this gradient image of the same dimensions as the original image. So if I could add them together directly, so there's a one-to-one correspondence between pixel coordinates and values, or I could multiply them. And so here I've multiplied them, and you can see it goes brighter to darker from left to right. And when you multiply that with the original, that's what happens to the image. The regions that are dark have a low value that is, say, 0.4, 0.2. So if you have a pixel intensity here of 240 and it gets multiplied by a 0.2, what do we get? What is that, 48? Yeah. And that would be pretty low on the intensity scale. What would happen if I added this? Just simple, not even a thought experiment, really. Does anyone want to volunteer? The graded component, guys. Well, so when you're multiplying it, these are fractional values from 0 to 1. So whatever's right will remain as is. But if you add it instead, then the left half of the image will get marginally brighter, and as you go farther right, nothing changes because you're adding only 1, which isn't really a lot to change things on the scale of 0 to 255. And the right half, by the time you get to the right end of the gradient, it's just a 0, so nothing changes. Color transforms. These operate on all channels. These are still point operators. Owing to the way images are formed, the values in the 3 channels are usually very correlated. just because of the nature of the objects that we image, since they all have very distinct boundaries, we end up with very correlated images. To brighten an RGB image, you would add a constant to all three channels. And there's a couple of side effects of doing that that I can think of off the top of my head. Does anyone want to guess what could go wrong? We already talked about one of these last class, sort of, tangentially. What happens if I add 20 to all three channels? Yes, color changes. It affects the hue and saturation. That's one. Um, the other possible side effect is that you could end up going above or above if you're adding, below if you're subtracting, whatever the acceptable range to visualize it is. So you might go above 255, below 0. So that's something that you would have to either clamp your values or normalize their values using the maximum and minimum and rescaling them to be in whatever the range you need is. So we know how to brighten an image that's RGB. To tint an image, how would this have been done? If I want to tint an image blue, I'm basically increasing the blue values. So I take all the values in the blue channel, only add my constant to that, and your image gets a bit more blue. Compositing and matting. This is a pair of operations that you would use if you wanted to separate an object from its background and take the foreground object and plug it into a different image. You could, how do you define the region where your foreground object is solid, sort of, or the parts that you want to keep? Those are represented using what's called an alpha layer. And the alpha layer represents the contribution of that particular signal. So this is a representation of how much we want the little bear guy to contribute to the target image, and we take the complement of that, 1 minus alpha, for the background. So the dark regions here get bright regions get dark. And then for the actual foreground object, we multiply it by alpha as is, because that's the region that we don't want the foreground to contribute to. And then add the two together and you get a blended representation. And PNG images also tend to have this alpha channel sometimes, especially the kind that if you've ever tried copying an image into PowerPoint or Word or whatever, and it's this object and you have a transparent region around it. Some image viewers, when you open those up, it will show a gray checkerboard background for that. Those images are said to be alpha matted. And this equation is a representation of the same process over there. You have the complementary contribution, and then there's the background and foreground images. Histogram equalization. This is a very cool approach to balancing contrast, sort of. The way you would do this is by calculating a histogram of pixel intensities for the entire image. Before I go into that, the reason this is cool is because for all the examples that we talked about so far, we were talking about adding a constant value to make it brighter, or a gradient. So you would need to know what you're trying to add to the image or take away from it. In this case, you don't have to know how to, what values to add. This is a way to estimate a better set of values. And it does that by generating the histogram. So here I've bucketed them into, I think, 34 groups. Normally it's done individually. This is just so it's easier to visualize. And what this represents is, if you can see at the bottom, there's 0 to 8, 8 to 16. Those are pixel intensity values. So there's a lot of dark pixels in here, about a 10,000. And that sort of dips. And then we have a few bright pixels at the end. So there's this big sort of gap between the distribution of dark and bright pixels. And ideally, we want this spread a bit more uniformly if we are to have better contrast and brightness. So we take pixel values that are either end and move them towards the middle. How do we do that? We break down the histogram equalization equation. We have C of I, which is the cumulative distribution function. And I'll show you what that looks like in a bit, but basically what it is for each value, so we have 10,000 over here for, let's assume this is just for the value 0, and then after that, pixel value 1, there's nothing. Pixel value 2, there's about 8,000. So by the time you get here, you would add up whatever the counts are and just keep summing as you go forward until at the last pixel value you have, that adds up to however many pixels you have in your image. So that gives you the CDF, and you do that, you normalize it for however many pixels are in the image, and that gives you what the new histogram would look like. Using the CDF. So we do this iteratively for each intensity value, summing over the previous ones, which is where the I-1 terms come from. The 1 by n is to normalize it by the number of pixels. And what that results in is, if you look at, so this is the CDF that I was talking about. We start with pixel intensity values and then keep summing up the number of pixels. And ideally, we want that to be a flat diagonal line. We're able to adjust this using this, and then we use the values here as a lookup table to find what new pixel values would be in the equalized histogram. In simple terms, we count the number of pixels, generate a histogram, take the cumulative sum, multiply it by your maximum intensity, and divide it by the number of total pixels. these two steps are to normalize it, and that gives you your new histogram. So we're able to do all of these things with just individual pixel values without looking at neighbors. When there's a huge variation in how the image manifests from region to region, or if there's objects that are very local to part of the image, then you would want to do things in a more neighborhood aware sort of fashion. One of the operations that improve on the histogram equalization that we just looked at is by doing it for blocks of the image rather than the entire image. In this case, you would determine pixel values by their position within a block and looking at comparing their values to the corners of the block within which they are. So you have a measure of distance from top left, top right, bottom left, and bottom right effectively, and that influences what the final value would look like to for each pixel. And once you do that, you end up with a better representation of what you're trying to do, since it takes into account variations between regions. An example is of a pixel that is, so here in points, when we're dealing with pixel values within a block, we would have to calculate the equivalent fraction for their position within the block. And once you plug those in, there's 0.3 and 0.7. You get the corresponding coefficients for each of the four terms, which is the four corners in the block, and that would give you your final pixel intensity value. In addition to the one approach that we looked about, now we're getting into territory that deals with operations that are pretty much the foundation of everything that we do today. So you have, and this is sample image data that's a 3x3 grid. If you want to blur, sharpen, detect edges here, or denoise it, you would have to look at, you can't just treat each pixel individually. You need to know the neighborhood. And how would you operate on an image in a way that's neighborhood aware? You do that using what's called either a kernel, a mask, or a filter. This kernel, you would then apply it to every pixel in the image that you're trying to process. And the kernel also has a neighborhood. So each of these values will contribute to each pixel's value once it's applied to it. And you end up with a value corresponding to it at every pixel. And we'll be going into this in some detail. So there's two operations that we do using this approach of kernels and images. There's cross correlation and there's convolutions. Oh, this should be just, I'll fix this. This should be just correlation, not cross correlation. So with a filter like this, you are able to see how similar each region in an image is to a kernel. And we do that by multiplying element-wise elements of the filter, each element of the filter with one pixel value and its corresponding neighborhood, and then we sum it up. So G would be the result at position ij in the output matrix after applying the filter, which is H, and F would be the value at the position I plus U and J plus V. We would sum over all U and V from negative K to K. And that means we're iterating over K, which is the kernel size. So if it's a 3x3 grid, then you have a kernel size of 3, and that will, this will become a bit more clear in a moment once I show an example of convolution. But the operation basically involves taking this entire 3x3, putting it on 1 pixel, and then applying all of those values to that pixel using this. So we select a pixel, choose a neighborhood around it, which would be twice as large as the filter is, plus 1. And that's so that we're able to put every element of the filter on the target pixel. So it needs to move around the pixel. And then we multiply it, sum the products, and assign that to the output. So you can think of it as a dot product between the neighborhood and the kernel for each picture, for each pixel. And this correlation, we don't really use it nearly as much as we use convolutions, which is why I introduced correlations first, because the formula is pretty much the same. The key difference is that we flip the filter when we're doing convolution. Convolution, you filter that. There's this YouTube explanation by 3Blue1Brown. It's really brilliant. I really can't do much better in terms of explaining it visually than that, so I would recommend watching it later. An example, this would be pretty much the same thing that you would do in both cases, with the only difference being that you're flipping the filter diagonally when you're doing a convolution. So how it works is, this is the region that we would like to operate on that has actual values in there. And we have a filter that we will be convolving with it, which is the moving average. So this is a filter that would average the values of whatever pixels correspond to this region. I just want you guys to remember that this is what the filter contains, 1 by 9, and there's 9 pixels. So when you add it all up, it adds up to 1. And each pixel in the neighborhood contributes an equal amount to the center pixel, which is where the new value will go. So we take that and apply it to this, and it's all zeros in there. So 1 by 9 times 0 plus 1 by 9 times 0, we keep doing that, sum it all together, and we end up with a 0. We slide the filter right by 1 pixel, and now there's a new value within the receptive field of the filter, which is a single 90. So you have all the other pixels are still not contributing anything since they're zeros, but this, when divided by 9, becomes a 10, and then you add all the zeros and the 10 together, and that gives you a 10 in the target um, position, which corresponds to this pixel. So if you'll see, it's at the same position over there. It's averaging these values up and outward, basically. We keep doing that. Now there's 2 90s within the window. So when you divide every cell by 9, that gives you 2 10s. When you sum it up, you end up with a 20. We do the same thing. Now we have 3 90s. So we end up with a 30. It's still 3 90s, 30. And we keep doing the same thing. And we find that this region of bright pixels surrounded by dark pixels has averaged outward. Oh, I had a redundant slide. Okay. So based on that example, what do you think this filter would do to this image, that there's just a singular 1 in the middle? Sorry? Right. Why? Right. So every time we apply this filter to a pixel in the image, the only contribution is from whatever the center target pixel is. Since this would be placed on whatever pixel you want to find the new value of, and that's the only one that's contributing any value. So when you sum it up, it's going to be the exact same value. You end up with an identical image. How about this one? Any guesses? We see, have a 20, 36, and then my filter is 1 over here, 0 everywhere else. I take this guy, put him on this particular pixel, and multiply this value with everything here. So this 20 would shift over here. Sorry, my bad. This, when we're convolving it with the image, we start at one corner, work our way there. When it's over here, for instance, actually, I should add one more just to be able to. This is something that the reason why I had to add 2 more is something that will come up. So this is the first case, first interaction that we're going to get with this, where the filter's over there. So we get 120. The filter has a 0 over here. I should use like two colors maybe. Filter has a 0, the value over there is a 20, so that contributes nothing. Value over here initially was a 0. Filter has the value 1, so that also doesn't really do anything. So this is not gonna do much until we get to this pixel over here. So in that case, would be added triangles. So when it's over here, we'll have a 1 for the filter and 0 everywhere else. So this won't contribute anything. This won't contribute anything. The only thing that's contributing any signal to this particular pixel value would be the one to its left. So you end up with an image that gets shifted by 1 pixel. We we already looked at this one. This is effectively the same filter that I started off with 1 by 9 in every cell. It's just the 1 by 9 has been taken out. We apply it to the image, and then we end up with a blurred image. Sharpening is done by doubling the value of every pixel and then subtracting the average. And the reason that works is when you smooth it, that de-emphasizes edges. And if you subtract that from the original, you get what's called detail extraction, or it's alternatively called the high pass filter because it lets high frequency features pass through the filter. And then you take this and add it to the original and you get a sharpened image. So one of the issues with trying to apply this to an image is something that I had a little bit of trouble with here when I was trying to draw this out. To be able to apply, if this was at the corner, then you don't really have any values at the edge to work with. So how would you go around dealing with that when only a small part of your filter has a corresponding region in the original image? Any guesses? Thought I heard someone say, yeah, padding. What I did over here, or was trying to do at least, I just added a few more rows and columns, enough to fit my filter. Now, what values you plug in there is a choice. You could either choose to put all zeros over there. You can set a constant value over there. You could just repeat whatever is at the edge, just copy that value indefinitely. So you end up with the rows and columns that are at the edges just repeated upwards. Or you could mirror what, so you would take a value that is at the edge, copy that to one left, then you would take the second column, copy that to the second padded column on the left, and just keep doing that to mirror it. There's also wrapping, which is once you get to say the right edge, you would just um, plug in values from the left edge. So column 0 would go after column n, and then column 1 would be column n plus 2, and so on. Um, this would influence the output of whatever operation it is you're applying. So any guesses what would happen if you use an averaging filter on a zero padded image? What does an averaging filter do? Yeah, it would, it's kind of like taking a paintbrush, like the smudge tool in Photoshop or whatever, and applying it to the edges. So you're blending the values along the border. So since you only have zeros at the border, whatever is closer to the edges will get darker, kind of like a vignette. Uh, uh, I just want to take a quick look at what I have up there. Okay. So far, uh, does everything make sense? More or less. This will get a lot more intuitive once you actually do it in code. Um, and I will definitely whip up a document with examples for some of these to make it easier to visualize what's going on. But um, nothing would help you more than being able to see it happen, which the video I linked to earlier, he does a fantastic job of explaining it. Um, so we covered some intuitive filters so far. Nothing fancy in terms of what values were actually in the filters. They were like ones or just shifted from the center. We know that those correspond to pixel shifts. Those are easier to make sense of. Now, if we want to have a better way to blur an image, it would have to be more uniform. And a Gaussian kernel would let you do that. So it's a point spread function. The value of the kernel at position xy is represented by g, and sigma is the standard deviation. So it controls how big or small the spread of the function would be. And effectively, it assigns higher weights to pixels that are closer to the center, lower weights that are farther away. This is kind of similar to pi r, the area of a circle, pi r squared times 2 in the denominator term. So you can see why that would affect the radius of the how far it spreads. And then there's an exponential term which lets the value decay the farther out you go. When you compare this with a more discrete mean filter that we had earlier, you'll find that the way that it blurs is a lot smoother in how values are assigned. I thought I guess I left it out. Gaussian kernel, I'll put that in the example section. Okay. One of the cool properties of this kernel is that if you convolve it with itself, it's the same as convolving it once with a kernel of width that is sigma times root 2. And all of those filters that we saw so far can be chained together, and it's still a linear filter. But there's a few operations that we would like to do that depend non-linearly on pixel values. So the simplest example for that would be thresholding. Thresholding is, like the name indicates, you have a threshold value, say 128, since it's sitting between 0 and 255. You compare each pixel value with it. If it's above it, you keep it. If it's below it, you discard that pixel, set it to 0, which is what this represents. There's also median filtering, which is similar to the mean filter, but instead of equally taking contribution from the entire neighborhood, we only pick the median value from the neighborhood. And that's not something that you can represent as a linear operation, since you need to know what all the values in the neighborhood are, and you have to pick one. It's not something that you can chain operators together to find. And the median filter is good at removing what's called salt and pepper noise, and it's better at preserving edges since it doesn't have the blending sort of effect. That brings us to edge detection. And with edge detection, we're circling back a little bit to what we talked about in the first class about how computer vision came to be. And one of the first approaches that they took was representing objects with lines or with their 3D outlines. So using these methods that we've seen so far, not necessarily the same filters, how do we go about detecting edges in images? So this also ties back into thinking of images as signals. When you plot your XY coordinates and have your pixel intensities as the Z value, this loosely resembles the shape of the face. There's dark values, so this particular region of the eye is dark, so that's deeper than the region around it, which is bright. And this would be a case of an edge, right? So over here, what does that look like? Just physically, you have a plateau, and then it falls off sharply after that. They look like steep cliffs. What does the word steep describe? Yes, slope is something that we're pretty familiar with doing, I'm hoping, from geometry. So the slope of a function would tell you how quickly or slowly it's changing. And we do that by calculating the derivative of the function. So since it looks like steep cliffs, once you get towards the edge, the slope over there starts changing, and then you get to a point of inflection, and the slope again levels out. So the derivative would reflect that change in slope. And using these points of inflection, we're able to find where edges are, which brings us to the question, how would you differentiate pixel intensities? So we're used to thinking about differentiating things when they're continuous equations. Um, Images that we're dealing with are discrete, they're sampled points with discrete values. So we need a way to calculate the derivative in a direction, dis- use working with that discrete representation. So we take two pixel values and look at the difference between them. And as kernels, this is one variation of what that would look like. So you take contribution from a pixel on the right, contribution from the pixel on the, column on the right, column on the left, since we're dealing with uh, the x direction. And this would de-emphasize pixels that are on the left vertical orientation to whatever pixel we're looking at, and emphasize whatever's on the right, and sort of conforms to a straight vertical line. And this would do the same thing for the horizontal and would be applied along the y direction. So I have examples of those up after this, but an edge case to keep in mind is when you're dealing with a noisy image. So here it looks like there should be a sharply defined edge, but at the border it's a bit blurry. And how that shows up as pixel values is with a lot of these oscillations. So if you go from one pixel value here to the next one and try to look at the derivative, the slope would also have a lot of oscillations. So you wouldn't be able to confidently say where the edge is in a case like this. To deal with that, you would apply a Gaussian kernel to it, smooth it, and that averages out a lot of the noise, and it smooths your curve out. And then applying discrete derivative to it becomes trivial. You're able to find where the peak is after that. Discrete derivative can be performed as a convolution using the filter we just saw. Smoothing can also be done. Since we want to get rid of noise, we just combine the two operations. So you have your Gaussian kernel, and you take the derivative of that, and as you're going up and along it, you see that the slope here is positive and high. It gets here, levels out, and that dip corresponds to going over the peak of the original Gaussian. So the slope turns negative over here, and that is reflected by the dip in the first order derivative surface plot. And if you look at it from the top, then this is what it looks like if you want to apply it in the, to find edges along the x direction, to find edges along the y direction. And then you would sample this to form a filter of whatever size you want, which is 3 by 3, 5 by 5, 7, 7. Examples of applying them to images. So there's a couple of standard operators. There's Sobel, there's Pruitt, there's the Gaussian kernel, and there's what's called the Laplacian of the Gaussian. So all of these are emphasizing edges. If you look at the Sobel, it also doubles whatever is in the same row as the target pixel, in addition to emphasizing and de-emphasizing vertical edges and horizontal in the Y case. And the edges that are emphasized, those correspond to the kind of filter. So over here, you see a lot more vertical edges along this direction, and horizontal over here. Pruitt, since it doesn't have the doubling effect, the edges that you end up with are it doesn't add in any other background except for just emphasizing edges. These are still not the kind of edges that we want it to be, since it's not just a line, but rather it's at least a few pixels wide, right? We can't call this 1 pixel wide outline. So it's not an object composed of lines. How do we get it to 1 pixel wide? So we talked about slope and gradients so far. Slope, we took into account only the magnitude of the slope so far. So the Sobol, Pruitt, all of these have more to do with the sign of the slope, whether it's negative or positive, and the magnitude. But we are also able to calculate the orientation of the slope for pairs of pixels, or at each pixel on the edge, using those filters. And we do that by plugging in the gradient values along both directions and taking the arctangent for that pair of values, which gives us the angle. So I plotted the orientation of the gradient for each pixel along every edge. And what that then allows me to do is, if this is an edge that is more than 1 pixel wide, and we want to get the 1 pixel wide representation, we can look at every pixel that is on the edge along the direction of the gradient. So you know that there's an edge there because of the slope magnitude, and you know in which direction it is based on the angle that we calculated using the arctangent. And then along that direction, you pick only the maximum value and suppress everything else. And what that gives us is, it takes you from these multiple pixel wide edges that aren't well defined to single pixel. Now, there's still something left to be desired. These edges aren't very continuous. They're kind of fragmented. So to deal with that, we come to the final step, which is hysteresis. So we started with an image, we extracted edges, we looked at their orientations, suppressed everything that was not the maximum along the direction of the edge for each pixel on the edge. And then we take two threshold values. We mentioned thresholding earlier. You compare a pixel value with another value and do something based on how whether it's higher or lower. And we use two thresholds instead of one. So there's one threshold that would capture all of these. um, the values after non-maximum suppression and treat them as strong edges. And everything that wouldn't survive non-maximum suppression would get, we'll call them weak edges if they are above a second lower threshold. Um, and if it's below TLO, then we discard it below the second threshold. So we take what we then get from here, weak edges, and look at the neighborhoods for each of these edges and see if they're within, say, 3 pixels to the nearest strong edge. Then you convert it to a strong edge. If not, discard it. And that gives you better connectivity. And you end up with edges that look a lot more complete than just the non-maximum suppression. And it also flattens the values to one constant value. So instead of having varying brightness, you have a constant brightness for all the strong edges and weak edges that then get connected to it. The final thing we'll be talking about today is called the canny edge detector. And the cool thing about the canny edge detector is that it consists of 4 steps. And that's what we just did. The 4 steps, we find edges using a discrete derivative filter like the SOLO. Find the orientation of gradients, do non-maximum suppression, hysteresis, and that's the entirety of it, the 4 steps. And this is our first actual computer vision pipeline where we're taking an input object, combining, chaining together a sequence of operations that use some sort of filtering and gives us something meaningful from it. Next class, we'll talk about the Fourier transform, pyramids and wavelets, and revisit geometric transforms that we did, I think, second class, and go into some more advanced ones, parametric and warping. I'll add examples for what topics would you want examples for, or what operations? Do I just use my best judgment on whatever I think would require examples, or yeah, I guess I could start there, and if there's anything that anyone wants more examples of, I can add those in later. Is everyone signed up for Piazza? Okay. Yeah, just post on there if there's anything you want me to add to. Oh, and the Fourier transform, there's a link that I put in here, which is also by 3Blue1Brown. It's a visual introduction to the Fourier transform, which is very useful to have just an inkling of seeing it once will really help put things into context for next class. I think yesterday was the last day of ad drop, so I don't know if you'll be able to register for the class again, like going forward. I think it's closed. Oh, yeah.
So I spoke to my advisor, said that the instructors are on and
I mean, I don't have a problem with it. I don't know what the you're a grad student, computer science or a different major? What would Department of CSU? Okay. Uh, did she mention you? So it's a forced registration. Did that term come up? Okay, yeah, yeah. I don't have a problem with it. I think the only thing you need is like my approval. Yeah, just send me an email and I can respond to that. And then you can forward that to your advisor, get force registered.
So is the course like an exam based?
Yeah, the syllabus is on UB Learns. Oh, but you won't have access to that. I can email you a copy of the syllabus also. And yeah, so I'll just open it. Do you want me to put it up there or wait, I can't put it on this one. So the main things are there's going to be 4 quizzes that I consider a total of 5 quizzes. Yeah, I'll be taking the 4 best ones. There's going to be programming assignments, and some of them will also have a written component. There's a project that I think I'll start asking for proposals of what you want to build by about week 4, maybe, or end of next week, probably. I just want to cover enough to have a foundation that you can use. And there will be a final, which is on the last class.
Registering for my
Uh, Today is um, this is week 2, right? Yeah, I wasn't gonna consider week 1 because a lot of people added, dropped. So week 2 onwards, I'll look at attendance. So since you attended today, you basically get full on that front, assuming you attend everything. Yeah, list of topics and okay. Uh, that is something that I'm not. I'm just gonna follow whatever the professor who taught this last fall did. I don't know what exact scale he used. So I'm following Dr. Rathas. So it wouldn't be anything too different from what anyone else does in terms of where the actual thresholds for each letter grade are. And I'll probably curve it if everyone's having a hard time.
Even you will decide whether the curving or abstract.
At the end, once
Or-
the entire
or
Wha-
maybe
once
we
the
drop
entire
two homeworks.
no once the entire semester is done, depending on what the average total score is, I'll see if it's if the mean percentage. So that's usually how it's done for every class. You just add up a weighted total and see what percentage everyone is ending up at, and see the class average. And if it's lower than whatever threshold, then you curve up. I I didn't make it available yet because I don't know if I can do that since this is listed as a traditional class. I'll be talking to my mentor sometime this week, and that's one of the things that I'll check with them. I do have recordings though.
Because I missed the first.
Okay. Um,
It would be. Have it first.
yeah. Okay. I'll talk to my
Also,
advisor.
when we have within the assignments or when we have like specific bonus tasks associated with the assignment, just to like make sure.
Yeah, that's how it was done last year. That's how I plan on doing it as well. I just I'm working on the first homework. I just haven't decided what all sub problems I want to put in there yet. I think I'm about halfway done with coming up with the problem statement itself. Should be out tomorrow.
Yeah, thank you.
Yeah.
For,
How how familiar are you with Python?
reasonably good.
Have you done any NumPy?
But working computer,
Yeah, then you're not gonna have a hard time really. So once we get past, I think camera calibration, panorama stitching, those sort of things take some attention to what's actually going on under the hood, and how to like match up features with each other, all of that. But the actual project and it gets easier as you get farther along in the course, basically. These are the things that take you the longest to wrap your head around: convolutions and um, Fourier transforms, all of that. Once you're able to apply those things, then solving actual problems is simpler, I think. Yeah. Right. Yeah. Yeah. You're welcome.